Hi, everybody. Thanks, Adam. So as Adam said, I am Joshua Feingold. I am the Solutions Engineering Manager for Tom Sawyer Software. What that means very briefly is that I manage most of the customer-facing engineering efforts, such as customer support engineering, pre-sales demo work, that sort of thing. So just to give you a little bit of background about Tom Sawyer, we're a leading provider of software and services that enable essentially big data visualization applications and visualization of data where discovering the nature of relationships is important. We're specialists in visualization, layout, and analysis. We've been doing it for more than 20 years. We are based in Berkeley, California, but we have international offices in Australia, Israel, Latvia, Mexico, and Turkey. And because of that, we can actually offer 24/7 customer support. We are used in a variety of very large products that you may recognize with such vendors as Cisco, Oracle, CenturyLink, IBM. Um, we have very large scale applications and very small scale applications going back 20 years and starting later this year. So we are used throughout the industry, whatever your industry may be, if it uses visualization, basically. So visualization, just to give you a very brief overview, is a topic that covers a lot of area. Just within the space of network design and network management, it can be used for design, monitoring, capacity planning, performance monitoring and management, inventory management, and automation of networking processes. In the broader context, anytime you have any piece of data that is related to any other piece of data, either directly or through an implicit logical connection, visualization can help you understand that data better from a human context, and also by giving you a graph on which you can then perform more rigorous analyses. So what we're here to talk about today really is Neo4j. Historically, Tom Sawyer has been able to connect to all sorts of back-end data stores, be they XML or RDF or anything else. But we've got this new capability for Neo4j that we're really excited about because obviously Neo4j is a a huge back-end graph-based data store, and now we have very easy integration with it, whereas before you had to do some custom work on your end, which we've done all the heavy lifting for you. So today we're going to talk about binding with your Neo4j database, how you define entity types, how you choose key attributes for visualization, defining rules to map your back-end entities to your front-end visualization objects, defining filters and search fields. And once you've done all of this definition of your visualization project, how to see the results of that on desktop or web. So I'm actually just going to jump right into a demo. Here is the Tom Sawyer Perspectives designer. What you can see here is our a project. This is a definition of a project. We have a schema, we have integrators, we have drawing templates, we have definitions of various views, filters, and search defined. And all of this doesn't seem terribly meaningful yet, but let me just jump into the end result and we can talk a little bit about it. So here I'm launching an HTML5 preview. So this is a preview that is automatically generated from this XML project definition. And what you see up on the screen here, you see a drawing view here, right? So here we've set this up with a seed query to load information about the Matrix movies from the Cineast database. Cineast is one of the canonical examples that's referenced on the Neo site. It makes kind of a nice demo piece. So here you can see we've done a pretty basic query, right? And if you're familiar with Neo4j, you're probably familiar with this interface. And basically, the query that we've run is this match movie, where movie.title is equal to the matrix with some modifications on it, and return the movies. And here is your Neo4j default interface. And this isn't really a customer-facing interface, right? You can use this to see data and the results of queries, but it isn't meant to give you the deep, rich, interactive experience that you can get with a full visualization product like Tom Sawyer Perspectives. So you can see that these have very plain UIs. They're labeled with their IDs. All of this data is in this properties inspector over here. So let's look a little bit at what we can do with the perspectives view. So now, instead of having all of this data kind of wrapped up in a details view, we can see that these are movies. Right? We've got a little movie icon. We can see the genre. These are action movies. This Matrix Revisited is a documentary about the making of the Matrix. We've also got this directed by information that we haven't loaded yet, and this rating information that we haven't loaded yet. We have release dates. So let's do a little bit of exploration just to show you what we can do. So now let's go ahead and find some data. We've defined this find data function that is going to run supplementary Cypher queries. And now we've loaded a stack of additional data. And with that data, let's go ahead and hit the canvas to show all of it. And here are a bunch of actors and actresses and directors that are associated with these movies. So this is run additional Cypher queries. And let's just go ahead and get a new layout while we're at it, right? Because now we've added a bunch of data and we want to see it laid out in a way that's nice and informative for us. So now we can see some clusters. We can run layout in a variety of different ways. You can see a nice hierarchy view, right? And we can see an orthogonal schematic. And so now we have, instead of just movies with little circles or circles representing actors or directors, we can see that this is a director because he's got a little star on him. We've got Andy Wachowski, we've got Lana Wachowski, right? So we can see basically what's happening here. So let's jump back into the project level and talk about how this all happened. So here we are back in Designer. Everything in Perspectives starts with a schema. Neo4j obviously is schemaless. However, in terms of defining your visualization, there are typically a set of core attributes that you know you're interested in looking at, right? So fundamentally, there could be additional attributes, but for the purposes of your visualization, you tend to know ahead of time what are the key things that you want to have visually shown inside of your drawing, right? So, you know, things like the genre, things like whether it's a movie or an actor or a director, things like the release date, things like the Rotten Tomatoes rating, right? These are all things that you know you're interested in visualizing ahead of time. So you can create your schema based on these few core attributes that you're really interested in seeing, even if you have more on the back end. Right, so here we have, you know, we've got actors, we've got IDs, you know, we've got the birth information loaded from the database, and then we compute the birthday based on that, right? So we're gonna just like format that. And, you know, that's pretty much what you would expect with actors, movies, and directors, and links that are accent, directed, and actor gender, which is something that we'll get to in just a minute. So we said before that we need to bind to our database, right? Localhost 7474, right? Just over here. We're giving the browser version. And here we're going to connect to localhost 74 DB data. We're going to test the data source. Looks like it's opening correctly. It's reassuring. We're going to look at some of the data bindings. So let's look at this movie. Right, so here we have this match movie where title is equal to my search characteristic. And this search, you can see, is in these pointy brackets here, or braces, that denote that it's not really part of your inherent Neo4j query language. This is saying that we've got this parameter that we want to connect to our model. Right, so we've got the backend Neo data model, we have an in-memory data model, and this is the transition between the two, right? So backend Neo data model, in-memory data model, and then we map from our in-memory data model into visualization objects like these nodes. So this query actually should look pretty familiar, right? We're doing a match movie where movie title is equal to approximately the search value, and we're going to get these attributes on it. All right, so we've mapped these this movie.id, movie.title, movie.release date into these tables, which you recognize if you've worked with Cypher query language very much, right? And here's the ID, and we're just telling this based on this query result. These are the in-memory data objects with these attributes that you're going to define, right? And just to look a little bit about this, right? So here we're defining this search parameter that we see up at the top. And the value is going to be this question mark I, which means to ignore case, dot star, which means is a wildcard, the value of our search attribute that we are defining in the model, and this dot star again for another wildcard, right? So that's how we're grabbing our matrix movies, because our search attribute in the model, which we can go look at, right here in the schema, we have this model attribute search, and we're setting it equal to this matrix, right? So we jump back into Safari, you can see the same query exists right here, right? So this is doing the exact same thing. We also did some data exploration, right? We can click on Andy Wachowski and find out some more stuff about him. Just snap that into our frame, right? So he also directed Bound and Speed Racer, right? So how are we doing that? So we've got a couple additional Cypher queries defined, right? We've got this, so this is our base Cypher query, and then we've got our additional Cypher queries which are connecting to the same data source. Right, and so this is showing, grab that the actor acts in the movie and return this same type of information, right? So it's just another Cypher query, exactly the same thing you'd be familiar with. We're also connecting to some additional information. So we've actually created a table in Excel to show actor gender data. Right, and so this isn't real data. This is a table based on the most probable gender of a given first name, right? So this isn't doing real stuff. This is just some dummy data we drew up, but you can see that we are actively tying in data not just from a Neo data source, but actually from Excel. And Excel, in addition to Excel, we are doing things like, if I click on Matrix Revolutions, you can see that I'm pulling this movie poster and this rating, which are not built into the database, directly from the Rotten Tomatoes website about this movie, which we have been linked to from data in the database. Right. So here's the IMDb. I guess it's IMDb ID. This must be the IMDb rating. Talking too fast, getting ahead of myself. But yeah, so this is the IMDb ID. This tells us where we can go get the rating. This tells us where we can go get the movie poster image. And those are what you're seeing reflected here. So you can use this visualization to take your Neo data source, which contains a great deal of information, gives you really fast queries, and tells you almost everything you need to know. And then you can supplement it with additional outside sources of information that could be contained in a different Neo database, or on a website, or on some small supplementary data file like an Excel file. Right? So however it is that your data is distributed, you can grab it from all over the place and unify it in a single visualization front end in the data model. Right, so once we have this data model populated from whatever sources we're interested in, we need to define how we're going to show that. So here we have some templates, right? So a drawing template defines all of the types of UIs that are going to be available in a view. Right? So here we defined an actor node. This is just the default, right? So here we know it's a male, here we know it's a female. This is just for generic if we don't have any gender information from our Excel file. Here we can see directors working the same way in movies. And what we're doing here are defining specific attributes that we're interested in showing, right? So for example, this is saying, this is the text on this node, this is just a default icon with a label, and the name of this is defined by the name parameter that we have drawn from the database, right? And same thing with the movie, a little bit more complicated, right? So here we're doing a kind of if statement. So we're going to check if we have release date information, then we want to show the date. And if we don't, then we'll just say that there is no data about it, right? So this is all written in a fully documented function language that we use within Perspectives. Right? So right inside of here, you can design and get documentation for all of the different functions that you have available. Right, so once you've got your data, you've got your schema, you've got your data that you're pulling into your schema, you've got your templates that you're defining, you can define your views, right? So if we jump back here, we have a drawing here, we have an inspector here, and we have a tree here. Right, so here in our definition, we've got a drawing, we've got a tree, we've got an inspector. Here in the definition of the drawing, we have rules. You can see they're the same types of rules for trees. And fundamentally, we do the same thing in every view, which is we define for every actor, which is an actor data element that we've loaded in from our backend data sources. For every actor, we're going to add a node. It's going to have this ID. We're going to apply some template, and here we're going to base that template on the gender of the actor. Okay. And we're going to give it the actor tag so that it knows what kinds of context menus it should be associated with. And if this is new, then we're going to set some properties on it, and we're going to go ahead and set some additional layout and positional properties on it, right? So this is showing basically the approach, right? So we've got add a node, here we've got this acts in, and we're going to check that the to and the from both exist, and if they do, we're going to add an edge, right? So fundamentally, very simple process, right? So backend data, in-memory data, front-end data objects. And once you've got that, you have a very powerful fundamental design that you can use to unify, visualize, and understand your data. So let's talk a little bit more about some of these other topics. So we also have, down below here, we have filters, which allow you to, at any point, grab which types of people you're interested in seeing. So for example, if you wanted to only see actresses or you wanted to only see actors, you can define a filter that uses the gender information to hide one or the other dynamically at one time. Right? And here we have a search. So here we've got a search definition. If we're going to search on movies, we're going to look for the release date, we're going to look for the genre, and we're going to look for the title, right? So if I click on our search bar here, we can go ahead and say, I want to look at all the action movies. Okay, so we've got Speed Racer and the Matrix films. Pretty cool. It automatically pans around as I select it in the dropdown. Let's say I want to search on something else. Maybe I want to view films from the 90s. Okay, well, we've got Bound from 96 and The Matrix from 99, right? Or I want to search on Mr. Neo himself, and there's Keanu Reeves. And you can see this is all completely linked together. You can see them highlighted here. We zoom to them, and in addition, we have this additional information out on the side. All right, so this oh, and we might as well show you how you can use this additional search feature as well. So remember that I said that we started the search with the matrix. Let's go ahead and add in another of my favorite action movies, right? We got Terminator. Let's go ahead and see where that brings us. Okay, so now we've got these 5 films that have Terminator in the name. Let's load some additional data. Areas over here. And we have this URL associated with it, which you may remember. And let's say I just want to go straight to the IMDb page. I also have actions that can allow me to do that. All right. So now we've got all this data. We can explore it interactively using the power of the Cypher query language that you're already familiar with. And we can interact and perform layout and see all of this information. So let's talk about some more industry-specific examples that may highlight some of the power that you can get from perspectives that you don't necessarily see in a generic example like this. So these are not going to be running from a Neo data source, just because the Neo database that I've loaded into memory is this movie example. But we'll go ahead and show you an area because fundamentally all of these things could be done like that. So I'm just going to give you a brief overview of some of these examples we're going to talk about real quickly. Right, so we're going to first look at a cable schematic and talk about the power of automated layout. So let's jump in and do that. Right, so if you work in the networking industry, you are probably familiar with cable schematics, right? And just for the sake of novelty, we're going to go ahead and we're going to launch this one as a desktop preview instead of a web preview. Right, so here you can see before we had loaded that in the Firefox browser. Those are all, that's all native HTML5 and JavaScript. There's no plugin required. Nothing is going on except fundamentally the process running in the processing going on the back end, and then being represented and drawn in an HTML5 canvas in the browser. We're a little slow here. The GoToMeeting software tends to slow down the processing a little bit. But when you have a cable diagram, if you work with these a lot, you know that they show the connections to and from within a cable connection box, and that you need a very specific type of diagram to show off that information so that technicians can use it, so that it's documented for future reference, so that people who try to make changes are making the right changes. And typically these are made by hand by a designer in CAD software. Let's see what this is thinking about. And what that means is that you have a static document, someone takes it into the field, they manually make changes to that document, and then when those changes occur, they need to be reflected in that drawing, and then the drawing, and then the specifications get brought back to the CAD designer, and then the CAD designer, updates the document, and then you have a new static document. Right? So this is obviously not a terribly efficient way to do things. Here I'm opening up the cable schematics project definition file. This is a .tsp, which stands for Tom Sawyer Project. All right, so let's try this. See if GoToMeeting will cooperate with me this time. Here we go. And this is loading data from a backend data source and performing layout. And this is a pretty complicated layout, so it will take just a little bit longer than it did to load the movie example. Right? And here you can see it just took us a couple seconds to load, and ordinarily it's a little quicker. That we have this rather complex orthogonal layout. There are many constraints that define the order that these nodes need to be in, right? So these are ordered numerically from these are ordered numerically from top to bottom on the left. Right, and every position and every ordering is important, right? So we've got these clusters define where these links go, right? So this is the block, the port, the box, right? And we can also dynamically explore, right? So I want to go from, so we're at 15,005, and we want to go back to 12,025, right? So let's go check this out. We can follow the link back to its origin. Right, so we've got these very complex schematics that have gone from being a static document that needs to be manually generated and then changed and then regenerated and then changed again into something that is fundamentally being driven by a backend data source. For example, if you have this in your Neo data store, you just run your query, you automatically generate your diagram, and once the diagram has been generated, it is there. You can modify the backend data source, or if you set up your project to do it, you could even modify the lines that exist inside this drawing, draw a new line, do a layout again, and commit that change back to your data store. And now, instead of working with these static documents and needing multiple people and multiple check-ins to your repository of drawings, you actually just have a live document that people can interact with and update in seconds and just save yourself a lot of time and aggravation. So let's go ahead and close that one down and bring up another example. So the next one we're going to hit is a microwave network analysis. So what we're going to look at is some data from a mock microwave network for cell phone carriers. Right, and here, what we're going to really look at is the density of data that you can get with visualization that you plan out well and really think about. Right, so here we have a network map. It's going to be loading here in a second. We've got a table view that's showing devices, connections, antennas down to the bottom. Right, and we also have equipment and settings. Right, so we have lots of buttons that we can turn, and we have an inspector in addition to that. So if I go ahead and click here, right now I've selected a connection. You can see that this table has revealed that connection, and these are the attributes. All right, so let's go ahead and zoom in and see what we're dealing with. Get a little closer, right? And let's jump in and look especially at this node. All right, so we can see that we have a bunch of connections coming in and out of this node. They're all different colors. They're all different weights. So what's all that about, right? So when we select here, we can see that our E1 is 40, requirement is 18, so we're using 45% of it. And we have this smaller yellow line, right? So we're using 75% of this one, and it's only got an E1 of 8, right? So its capacity is much lower, and it's being used to a greater extent. So the line weight is thinner, and it is a redder color, right? So here you can see where actually we are controlling dynamically the way that usage is represented. So right now we've got like some blues over here, right? So this is a low load, right? And here we're getting closer to like a teal. well, maybe we've got our colors and we want to change them. So this is all being controlled dynamically. So let's say we go from a dark green to a light green. So now the drawing has been updated to reflect the choices that I have made dynamically by modifying in memory uh, the parameters that I'm using to drive this visualization. Right? So this is all coming back to having this central data model that goes between the backend data source, which is containing these links and these towers and the antennae on each of these towers, uh, and the front end, which are the nodes that we're looking at, right? So even though we've got a front end and a back end, we've got this control of data in the middle, which allows us to do a lot of really powerful things dynamically with the visualization. Right? And so even more so, let's zoom out. And let's say I want to run some analyses to find out what's going on in this network more than just looking at a static view of what is the present loading on each of these connections and how are these devices connected to each other. Let's get some deeper insights here. So we've set up some analyses to run here. So this is just a simple clustering algorithm. What we're going to get are clusters of maximum internal connectivity and minimum connectivity between clusters, right? So, if you're kind of just looking at this drawing, maybe it's tough to tell why these are the way they are. But you can inspect this to see that, in fact, these are logically distinct. These towers are adjacent, but that doesn't mean that they are strongly connected to each other in the broader scheme of the network. They exist in different clusters. And in fact, we can reveal those clusters with uh, which will turn those clusters into circles, which will then be laid out so that we can view them nicely, right? But this isn't a nice way to look at the network. It's too big, takes up too much space. Let's go ahead and jump back to the schematic view. So we also have ways to analyze the network based on connections that are more direct, right? So you may want to find out how the connection from this node over in this green cluster, right? So let's find out what cluster that is. Looks like that's cluster 3. Let's go ahead and start that, set that as a start node for some analysis. And over in, let's see what cluster this is. Cluster 8, cool. So we've got these two clusters, and we want to find out how strongly connected they are. So let's go ahead and find what's the shortest path between them, right? So now the information that we're interested in is this one linkage, right? So we want this one shortest path to stand out, and all of the data that was driving the colors of all the lines is still there. We haven't changed it. We haven't modified anything. We just set a switch that says the thing that we care about right now is the analysis results, not the weighting based on usage, right? So again, using this intermediate data model, we get to see very quickly and very easily the results of an analysis that we can just toggle on and off, right? So we can clear away all these analysis results, and now we're back. Let's say we want to paint these connections again. Right, so now all of our data is back. And just for the sake of curiosity, let's run a couple more analyses. I'm gonna go back and select these again. So we got this one. Here's our start. I don't remember which one was our end. Let's call it this one. Here's our end. And let's look at all the disjoint paths, right? All the paths that require using none of the same edges. Looks like we've got several here. So we've got this purple path that loops way around the network. We've got this uh, fairly direct orange path that doesn't seem to go too far out of its way. We've got this green one that looks like the most direct of all of them, and then this pink one kind of meanders its way through the network. And again, if we're really interested, we can even follow these links, right, with our link navigator tool and jump from one to the next, just like we did with our actor connections. And finally, we can look at minimum cut, right? So now this is showing us what is the smallest number. Oh, and we would have to cut 5 distinct connections within this network to isolate one tower from the other, right? Because these are showing up in blue, everything else is gray. These are our key connections right now. So you can see that those two towers are actually pretty robustly connected. We've got a bunch of disjoint paths. We've got five connections that would need to be cut in order to isolate them from each other. So yeah, you can see that just by changing what data you display and adding a couple linked views, right? So this table with additional information, this attribute table that shows an inspector view, trees, and having drawing settings and connection and device information over here, right? You can actually get a lot of data in a very compact space that's still comprehensible to a human being, which is the entire goal of visualization. Right, and so let's jump to one more example. And this is going to be our governance example. And we're going to show off driving multiple topologies, which I misspelled, and social network analysis. Okay, so let's go ahead and grab that. Okay, so let's go ahead and launch this one. And this example we're about to view uh, shows off the connection. This is, data that shows the boards of directors of some publicly traded companies. And here we can see a view that you might have in your database, right? So here are individuals and companies together. Let's zoom in here and just view a little cluster. Here you can see we've got this Continue Care Corporation and some of its boards of directors. And there's some members of its board of directors. And we've got this Neil, who is connecting Continue Care Corp, RE Systems, and IVAC Corp. Right, so we've got this concept of a person being connected to the company on which they are the board of directors. Right, so this is very much a graph database type idea, but using this same data, we can create a second topology. Right, so instead of viewing people as connected to companies, let's connect people to the other people who are connected to the same company as they are. Right, and so now instead of having this sort of mixed bag, we have all people and we have a social network. And when you have a social network, you can do all kinds of cool social network analysis on it. All right, so let's check out what we can do. So here we've got this tree view. It's empty right now because we haven't run any analyses, but let's run some centralities. So here we've defined 4 actions that are the 4 most common social networking, 4 most common social networking centrality algorithms. We'll just go ahead and start with a betweenness centrality. All right, so betweenness centrality measures how many shortest paths a given node lies along between other nodes in the network. It's probably the second most common of the advanced social networking centrality algorithms. It's probably the second most commonly used. So when this finishes running, we can see that we have filled in this tree on the left. So we've got this Marshall Geller guy. He's pretty cool. He has a normalized importance of 100, or a normalized centrality of 100. We've got this Lawrence Schafran, who's 47. Let's just go ahead and select him, and we'll jump right to him in the drawing view. All right, here's Lawrence. Let's go ahead and zoom in on him. Here he is. So you can see that Lawrence has had his background set to red, or to a light red because he's a moderately cool dude, while his neighbors have their background set to white because they are not central within the network. Right? And we can see that he is marginally larger than his neighbors, but Marshall Geller, who is, the most connected in this network, is substantially larger and has a dark red background. All right, so just for the sake of curiosity, let's go ahead and run another centrality measure to see if we can get some different information. So we have Marshall Geller, Lawrence Schafran, and this Jerome Feldman guy. Go ahead and run closeness. And now we can see the things are looking pretty different, right? In terms of closeness, which is a ease of reachability measure to other people in the network, it's a much flatter distribution, right? Jerome Feldman is now on top. Marshall Geller is way down here. So depending on the type of closeness that you're interested in, you could get some pretty different results. So actually, maybe we're not even interested in just different types, but in different subsets. So if we jump back to betweenness really quickly, right? So this is giving us the betweenness centrality based on the entire network. But maybe we aren't actually interested in the entire network. Maybe what we're interested in are the people who are connected to multiple companies, right? So anyone who's only on one board of directors, well, maybe we're willing to discount that person as not that exciting for our purposes, whatever our purposes are, right? So instead of being on one board of directors, we want to only view everyone who's on 3 boards of directors. Now that changes our topology somewhat, so we'll go ahead and run a new layout, bring everybody together, and you can see, this is our layout, or this is our analysis result from the entire network, but maybe it'll look a little different, right? So we had Geller, Schafran, Feldman, and Radzik. And now we can see that it's Geller, then Feniger, Cantor, and Greenberg, right? So this is an entirely different set of people that, you got your data from your backend data source, but now you can learn different data without having to, run additional queries or worry about, defining different topologies. You can just use this dynamic filtering and dynamic analysis to find out that other information you need.